Entropy? Does that word sound familiar to you? If so, you might agree that it's one of those terms that makes you scratch your head, wondering, what does it really mean? And no wonder. Entropy is often one of the most intricate and, let's be honest, somewhat poorly explained concepts in the vast universe of science. But why is it so confusing? Well, part of this confusion has historical roots. Can you believe it? A long time ago, rather questionable choices were made when it came to naming this concept, and these choices persist to this day. Now, I'm not here to delve into the historical details or the academic disputes surrounding entropy. No. What I want to do is explain to you, as clearly and simply as possible, how entropy is actually a statistical quantity. And more than that, how from this understanding, the second law of thermodynamics not only makes sense, but reveals itself in an almost magical way. Imagine entropy as a super nerdy way of telling stories about atoms and their adventures in infinite arrangements. So what does statistical quantity mean? Sounds like something you'd ask on a date just to impress, right? But let's make it simple. Imagine that entropy is a way of counting how many possibilities there are for organizing the atoms in a substance. And believe me, it's not something you can put in a jar or squeeze. Let's play around with it a bit to get a better understanding. Imagine 36 coins, all identical, each with a green face and a yellow face. Let's arrange them in a perfect square, 6 by 6. Now, think of all of them with the green side facing up. If I ask you how many ways there are to achieve exactly this configuration, would you say? 1, of course, and you'd be absolutely right. But what if we turned one of them over, leaving a yellow one in the middle of 35 blue ones? How many possibilities would we have now? The answer is 36, because we could choose any of the coins to be the rebellious yellow one. This count of possible configurations, or as scientists like to call them, microstates, is what gives us the famous W. In this case, W and 36. But that's where things start to get interesting. Increase the number to 3 yellow coins among the green ones, and suddenly we have 7,140 ways of arranging them. Sounds like someone at the party got a bit more excited, doesn't it? Now, if we get really bold and change it to 10 yellow coins, hold on to your chair. That jumps to a number that I promise I won't try to say out loud, but it's something like 254 million ways. That's right. And if we think of 18 coins of each color, the number of possible arrangements explodes to something like 9 billion. If we tried to show one of these configurations every second, we'd need 300 years to see them all. That's without coffee breaks, eh? And when we start talking about gases with an absurd number of atoms, like 10 to the 21st, things get so surreal that only statistics can do the job. The next time someone mentions thermodynamics at a party, you can just smile and say, "Oh, it's just a bunch of atoms trying to organize themselves at the physics ball." Imagine yourself now holding that favorite coffee mug of yours, the one that accompanies you on lazy Sunday mornings and evenings of study or work. Have you ever thought about the universe hidden inside it? I'm not talking about coffee or whatever you put in it, but about a concept that may seem like a big deal: entropy. I'm going to tell you a story that promises not only to grab your attention, but also to make you look at your mug differently. At the beginning of this video, we briefly touched on the subject of entropy, that number, or quantity if you prefer, that reveals the possible ways in which the atoms of an object, such as our coffee mug, can be arranged. Using the example of coins, entropy was that number W that we calculated for each scenario. But let's go back to our coffee for a moment. It may seem incredible, but each sip of your coffee contains an absurd number of atoms. And even more impressive is to think of the ways in which these atoms can organize themselves without changing what you're drinking. This number, although gigantic, is finite. And guess what? It's the entropy of your coffee mug. Back in the second half of the 19th century, 3 super-intelligent physicists called Boltzmann, Gibbs, and Maxwell began to think about entropy in a slightly different way, using the kinetic theory of gases. These three are practically the godfathers of statistical mechanics. When you search for Boltzmann's entropy on Google, you'll find an equation that might seem a little intimidating: S and Kx log of W. And if you happen to pop over to Vienna and visit Boltzmann's grave, you'll see this same formula engraved on his tombstone. Yes, it's serious. But what does this logarithm mean? And who is this K? Well, imagine that, instead of one, you have 2 mugs of coffee. Because, let's face it, 2 mugs of coffee are always better than 1, right? If we want to understand the entropy of this new system of 2 mugs, we have to think of all the possible ways of arranging the atoms in both. Mathematics tells us that the total number of arrangements is the product of the entropies of the 2 mugs. But what if we were talking about energy? Then we would add up the energies of each, which seems simpler. And this is exactly where the logarithm comes into play, transforming the product of the entropies into an elegant sum. As for K, this is the famous Boltzmann constant, a key element that helps give entropy a dimension of energy per temperature, or joules per Kelvin, aligning it with the first law of thermodynamics. Sound complicated? It's actually quite an elegant and even simple concept when you think about it. And here's the hook. Unlike energy, which is conserved, it doesn't disappear, it just changes form, entropy is the rebel of physics. It is not conserved, it only increases. And that's exactly what the second law of thermodynamics teaches us. The entropy of a closed system, like the universe for example, never decreases. It only increases. This explains a lot, from why it's impossible to create a perpetual motion machine to, on a much larger scale, questions about how the universe evolves. So, have you ever stopped to think why physics is so amazing? As well as explaining why the sky is blue and why we don't fall off the planet, it has an almost magical ability to predict the future. Yes, I'm serious. Thanks to what we call the determinism of physical laws, scientists can know what's going to happen before it even happens. It's like having a crystal ball, but instead of magic, we use mathematics. But before you go around trying to predict the lottery numbers, let's add some spice to this story. Talk of reversibility and irreversibility. It may sound like the name of a new science fiction series, but it's a key concept in understanding how the universe operates. Imagine if we could rewind the universe as if it were an old movie. If we knew all the rules, the equations of motion, and the current state of the system, we could predict the future and reconstruct the past. This is what we call reversible theory. It sounds simple, but believe me, this idea of being able to go back in time and still keep everything consistent is something that makes a lot of heads spin. And for good reason. It implies that every moment in the universe is unique and has a history that defines it. Imagine if we could apply reversibility to undo those embarrassing moments in life, like sending a text message to the wrong person. Oops, let me just use my equations of motion here and that's it, as if it never happened. If only real life were like that, eh? Let's say we have 5 spheres of different colors. Each of them plays a unique role in our plot, representing different states of a system. Now imagine that these spheres are connected by arrows that tell us what the next step will be to reveal one of the most fascinating secrets of physics, the question of reversibility and irreversibility. Reversibility and irreversibility? But what does that have to do with me? You may be asking yourself. Everything, my dear viewer, everything. Because this is exactly what allows us to understand why certain things in life and in the universe only happen in one direction. Have you ever seen someone break a glass just by shaking the pieces? Haven't you? Well, the second law of thermodynamics explains why these things happen the way they do. Let's play a little with our colored spheres to get a better idea. Imagine that by following the arrows from the green ball to the yellow one, and so on, we create a perfect cycle. This is a deterministic and reversible system, where everything follows an order and can be rewound without confusion. But what if we suddenly couldn't tell where we came from or where we were going by reversing the arrows? That's where the drama of irreversibility comes in. A plot forbidden by the laws of nature, where each ball has its own unique and unmistakable story. Now for the icing on the cake, how this dance of colored spheres leads us to the second law of thermodynamics. Imagine two sets of spheres, one green and one red. If we start with the green set and over time find ourselves playing with the red one, this is nature telling us that entropy, i.e. the disorder of the universe, is only increasing. It's like the universe telling us, I prefer the mess, thank you. And before you think that 43% is a good chance of messing up the rules, let me tell you that, in a world of atoms and molecules, these possibilities are practically zero. That's why we never see a cup of coffee heating itself or a broken glass assembling itself out of thin air. And that, dear friends, is the beauty and the curse of the second law of thermodynamics, the unalterable direction of time, where every moment takes us to a state of greater disorder and tells us the story of the universe. So, as you observe the world around you, remember that every little event, from the simplest to the most complex, is taking place governed by the second law of thermodynamics. That, my friends, is not only an impressive feat of science, but also a tribute to our existence. Thanks for being with me so far. I'll see you in the next video.